Grade 11s, welcome to today's gas law lesson on Boyle's Law. Boyle was a scientist who was working on the gas laws. He's going to be the first of three scientists we're going to study. And he was doing a bunch of research comparing the space that a gas takes up and the pressure that is on it. Now he has this big quote that we've taken out of his research that sounds like a lot of gobbledygook, but really it boils down to this. Yes, bad pun intended. If we take a gas and put pressure on it, so here's a syringe that I might have a gas in that I put pressure on, and I put pressure on by weighting it down with textbooks, what we would see is that the amount of space that gas takes up, as the pressure goes up here, the amount of space that the gas takes up goes down. Obviously, you can imagine that the more textbooks that I would have on this syringe, the more it would squish the gas particles down in the container. Now, had we been in my classroom right now, we would actually be doing this. I have a syringe there that has the end plugged, and I've frozen it into a wooden block, and I would get you to weigh it down with textbooks and measure the volume, and then we would graph it. However, in these times, we'll just move on and talk about what would be happening. What we would notice is that if we have a given mass of gas, so we've got a fixed quantity, amount that nothing can go or come in, and we keep the temperature the same, that the volume of the gas, the amount of space it takes up, varies inversely with the pressure. Inversely basically is saying this: as one thing goes up, the other goes down. So if we increase the pressure, if the pressure goes up, we'd expect the volume to go down. If I reduce the pressure, if I let the pressure go down, then the amount of space that the gas takes up, the volume in milliliters or liters, whatever we're measuring volume in, would go up. This is an inverse relationship. Sometimes it's called a reciprocal relationship. Now, if we want to, we can think about why this is. In a big container, the particles of gas have a long way to go before they hit the sides of the container. If they're not hitting the sides of the container, they're not putting pressure on the container. So in a big space, there's very little pressure. The opposite's also true. In a small space, the particles are moving just as fast, so they will hit the sides of the container quite a bit and cause quite a bit more pressure. Take a look at this picture here. In both pictures, the amount of little blue dots representing gases is the same. When we have let this plunger go up, there's a larger space available, so the particles don't hit the wall of the container very much, and the pressure is low. If I push the plunger down, like I have in the second drawing, and the particles are squished closer together, because I put the pressure on it, the volume's gone down, and at the same time, the amount of pressure being caused by the particles has gone up. And you can see the measure on the barometer has gone up. So again, as one of these factors goes up, the other one goes down. This is that inverse relationship. So Boyle's Law explains how we breathe. While you're sitting at home right now, what I'd like you to do is put your hand right on your tummy and push your tummy out as far as you can. Try to make yourself look as fat as you possibly can. I'd be making you do this in my classroom as well, and you'd all be looking around going, I don't want to do this in public, so be happy it's a video. Push it out as far as you can, and then I want you to breathe in. Breathe in and in and in and in and in until you can't breathe in anymore. It's going to start to hurt a little bit down at the bottom of your rib cage. Keep going. Now, that hurting, that stretching that you're feeling is your diaphragm muscle. What you're actually doing is you're taking a muscle called the diaphragm, which is a big pancake-shaped muscle at the bottom of your rib cage, and you are dropping it down. That makes the space inside your thoracic cavity, your upper part of your chest, get big. If we have a big volume, the volume has gone up, then the pressure inside your lungs has gone down. Since air rushes from an area of high pressure to low pressure, the air comes rushing down from the outside into the area of low pressure inside your lungs. And that's how you breathe in. Well, now what happens when you want to breathe out? Well, now your diaphragm's going to flex the opposite way. You blow the air out. The diaphragm muscle pushes upward. That means the amount of space here is a lot smaller than it was before. And so the pressure inside your lungs has gone up, okay, because the volume space inside your lungs has gone down. Again, an inverse relationship. And that means that the pressure in your lungs is higher than it is outside your lungs, and that forces the air back out. That's how you breathe. You breathe because of Boyle's Law. Now, frogs do it slightly differently. Frogs don't have a diaphragm. Frogs have that big area underneath their chin that goes up and down, in and out as they breathe. Go to YouTube, unless you're watching this on YouTube after this video is over, Google a picture of frogs breathing and you will see that chin going up and down as they are gulping the air into their mouth. They're using their mouth to change the pressures to trap air and bring it up and to bring it down from their lungs. So how does this work for the math? Well, take a look at this container again. So we're assuming it's a fixed amount of air or any kind of gas. That won't change. And we've done some trials. When the pressure was 1 atmosphere, in this particular container, the volume was 800 mils. Now I'm using atmospheres, but we really could be using any units of pressure that we want. We could be using millimeters of mercury or kilopascals, but in this video, we're going to use atmospheres. So if I multiply these together, I get a total of 800. If I double the pressure, I put twice as much pressure down on the plunger, the volume reduces by half. Again, their product is 800. If I put 3 times as much pressure, 3 atmospheres, I have 1/3 the volume. 4 times as much, 1/4 the volume. No matter how I look at it, the product of pressure and volume is a constant. So pressure times volume in any one instance will always be equal to the product of pressure and volume in a second instance. This is Boyle's law mathematically. P1 times V1 equals P2 times V2. You have this formula on your cheat sheet, so on a test or a final, you'll always be allowed to have it. What I want you to do is show me you know how to use it. Let's take a look at a couple of examples. When we give problem-solving type of things in any kind of science, again, what I want you guys to do is go and look for the numbers. Include their units. We've got 30 liters, we've got 153.2 kilopascals. I'm just looking for numbers, 21 liters. Now I'm going to read, and I'm going to look for clues about what these things might be. If a gas sample possesses a volume of, oh, this is volume. We know liters means volume. That's the first thing that we know. We know liters means volume, and it tells us volume. So this is the first volume I've seen. So I'm going to label that as V1, because it's the first one that I see, at 153.2 kilopascals. Well, kilopascals is a unit of pressure. The word at is a linking word. It links these two values together. It means they happened in the same instance. So if this is V1, and I know this is a unit of pressure, then this will be P1. The question says, what will be the pressure? There's my unknown. If the volume decreases to 21 liters. Well, this is a new volume. I'm going to call it V2. So anytime we do a problem, it can be chemistry or physics, it doesn't matter. Look for the numbers and their units. Try to label them with the letters that represent what they're describing, volume or pressure. Then I want you to go to your list of formulas, of which we only have one right now, and write it down. Writing down the formula is almost always worth a mark to a chemistry or science teacher. It tells us that you understand what kind of problem it is. P1 times V1 equals P2 times V2. We're now going to substitute. What is it that I know? Well, I know P1. It's right here. It was 153.2 kPas. It's important, you guys, to include the units. That's a big deal. We definitely want to do that because it's going to help us make sure we don't make mistakes. V1 was 30 liters. P2 we don't know. That's the thing we're looking for. And V2 was 21 liters. Well, how do you do the math for this? You multiply what's together, the two numbers on the one side of the equation, and divide by what's left. What's left is 21 liters. On your calculators, 153.2 times 30 divided by 21. We're going to get an answer of 219. The answer is going to have to come out in kilopascals because the units on the left are always having to be the same as the units on the right. Now sometimes, and you're going to see some problems, I give you two different kinds of units. I might give you pressure one time in kilopascals and the next time in millimeters mercury. If I do that, you're going to have to change one of them. It doesn't matter which, just so that they're the same. Also watch the units for volume to make sure they're always the same. They don't always have to be liters. They could be mils, but as long as the units that were given on one side are the same as the units on the other side. Otherwise, nothing cancels. Okay, let's try one more example. What volume would a 62.9 liter sample, well, here's a unit and a number, of a gas occupy if its pressure was changed from 320 millimeters of mercury to 930 millimeters of mercury? So again, the first thing that I did was go and try to find out what are the variables, what is going on there that I can use. Well, I see that I've got 62.9 liters. So liters is my first volume. So what volume would this many liters of a gas occupy if its pressure was changed from? Well, this many liters was originally at this pressure. Millimeters mercury is a pressure, so I'm going to call that P1. And I'm changing that to 930 millimeters of mercury. So that's a new pressure. That's P2. Again, I need to have a formula that has volumes and pressures. And so I'm going to use the only formula I know, the one with volumes and pressures. P1 times V1 equals P2 times V2. So P1 was 320 millimeters of mercury. The first volume that was associated with it was 62.9 liters. These two cases happen together. The new reality is that I'm going to have 930 millimeters of mercury, and I want to find the new volume, so that's my unknown. I have millimeters of mercury on both sides. That's important. We have to check that. Again, if one of them was not the same, I'd have to change them, at least one side, so that they were the same. Because this side has liters, my volume will come out in liters. So I'm going to go 320 times 62.9 divided by 930. That gives me an answer of 21.6 liters. You guys, these answers should make sense. My pressure went up by about 3 times. So I'd expect my volume to go down by about 3 times, and it does. In the first example, my volume went down just a little bit, so I'd expect my pressure to go up just a little bit. If your answer doesn't make sense, you've probably done something wrong. And these answers should always make sense if we stop to think about it. Now, there's lots more examples in your textbook in Chapter 13, and there's a few questions that you can practice at that point. What I'm hoping that you've got from this video is that you can explain the relationship between pressure and volume. As one goes up, the other goes down, and explain to me why. Talk to me about what the particles are doing. I also want you to be able to use Boyles Law, the formula, to calculate pressure or volume as one is changing or the other is changing. What I'm going to get you guys to do to practice Boyle's Law questions is those textbook questions that were listed on your notes, as well as the questions called gas laws that you find on pages 9 and 10 of your workbook. Thank you for being